Hello, my name is Daniel Way, and my Colorado State University ECE561 project is a ukulele synthesizer. I've long been interested in building instruments and decided that this was a good opportunity to pursue that interest building a synthetic instrument. I wanted to create something that was very similar to a standard ukulele in both feel and sound. So, on the right you see my final product, and on the left you see a high-level system view. I opted for capacitive touch to monitor where the user's hand is placed, fed that back to a controller using I2C. I also took input from virtual strings, which are lasers focused towards photodiodes, and passed that back via PWM. The PWM is monitoring the timing, or how long the string is interrupted, to collect volume information. The microcontroller synthesizes a waveform using a wavetable oscillator and feeds that to a digital to analog converter and Class C amplifier via I2S. This is amplified through a speaker to produce the sound. This design also only uses integer math at runtime. For my development hardware, I selected the ST Microelectronics Nucleo 64 board. It has great power, 100 MHz ARM Cortex M4 processor, lots of flash, lots of SRAM, and all the peripherals I need. I selected powerful hardware because I didn't want this to become a bottleneck in the project. I also selected STM products because they have a great developer environment, and it was very easy to use their I/O configuration and hardware abstraction library to get going quickly. Time to market on this project was important as I only had a few months for the final delivery. For capacitive touch, I used the NXP MPR121 chip. It's very small, fits well into my final platform, and has 12 channels of input sensing. I built the capacitive touch sensors by drilling holes in the fingerboard and threading through bare wire, sandwiching it between copper foil with conductive adhesive backing. This was a little bit time consuming, but well worth it, as the raised wire almost simulates the feel of an actual string being pressed, a little bit of tactical feedback for the player. Fitting everything was a little bit of a trick with wire layout, but eventually I got it done. To hold the lasers and the photo transistors, which I got off Amazon, I 3D printed a couple different bridges. This on the left is for the laser diodes and has some holes to guide the wires. On the right, you see my photo transistor bridge, which has offsets to prevent the contacts from being touching each other or shorting out. Everything was wired on the back side of the soundboard for the instrument. I also used this digital to analog converter, the MAX 98357A, which is an excellent little chip. It can produce 3 watts of output and has a wide range of input, and a 300 kHz Class D amplifier. This was my first time using an I2S device, so I had to learn a little bit about the protocol, its 2 different clock inputs, and how the data bus works. Instead of writing to the output every single time step, I opted to use the STM32's onboard direct memory access, or DMA, to have a circular buffer that I would just feed periodically. This allowed me to avoid some high overhead from constantly activating interrupts and use that time for other parts of the system. Overall, though, keeping this buffer fed was over a third of the execution time. I did perform some tests to make sure I could produce a simple sine wave, and I also measured the output from an actual string and its sound envelope you see here. It turns out that the sound envelope is kind of like an exponential decay function, so I implemented that in the microcontroller so that my notes would sound more natural in how they slowly reduce in volume.
Here's my laser ukulele construction. I have these capacitive touch strings. Each is a piece of copper tape, and then a wire, and then another piece of copper tape sandwiching it. I have the laser diodes housed in a bridge that I 3D printed, and the phototransistors, which are also housed in a 3D printed module. Let's take a look inside the ukulele. Up here at the fretboard, I have 3 breakout boards, which are the NPR121. It's a capacitive touch sensor, each with 12 channels connected to wires that are on the fretboard. This is the circuit that is receiving light from the laser diodes. Under here you can see the power breakout for the laser diodes, and my Nucleo 64 board that's controlling everything, driving this speaker.
The wavetable class I wrote was my implementation of a wavetable oscillator, also called DDS in other systems. A paper I looked at used MATLAB to generate this. However, I opted for C++ with its const expert evaluation, so my table could be created at compile time and then written directly to the microcontroller. The technique is very simple. You have one wave period of your signal, and then you just index into that table, allowing the index to wrap around every time it would normally overflow. That way you're selecting samples at the correct frequency based on your reconstruction frequency and the pitch of the note you want to create. My wavetable, because it's const expert, can use double precision floating point mathematics. However, that is all done on the host computer when compiling and does not make it to the microcontroller. The final image on the microcontroller is just the data. I also included indexing into it, which all of these divides and modulo operations are actually just shift and mask operations, because this delta value here is always going to be a base 2, or a power of 2 integer. So the compiler can figure out how to do this very efficiently. This overloaded indexing operator performs interpolation and can take an index of any size. So if you wanted to quickly switch out to from a 16-bit unsigned integer index to a 32-bit unsigned integer index, you could do that without any modification to this class. Here's an example of indexing into the wavetable. Suppose we have a 64-element table and a 16-bit index. The software will take the upper 6 bits to directly access elements from the table. It will use the low order bits, these 10 bits, to interpolate between adjacent elements. It's important to have enough bits to represent the index, as otherwise you would get frequency quantization. Here's an example. Supposing a reconstruction frequency of 48 kilohertz, and we want to play a 440 hertz note, an A4. Well, that would result in an increment every time we sample the wavetable of 600. That's not high enough to actually make it into the direct index range. So if we didn't have these low order bits, then we would never actually be incrementing our counter. If we do have the lower order bits, these would accumulate over time, and we would start to accumulate changes in the direct index range. Likewise, if we had a G5 note here, that would have a bit in the direct index range, but these low order bits are also important, as without them, we would not be incrementing the counter by the proper amount, and we would actually end up with a pitch different from the one we are trying to produce. Linear interpolation was important inside the wavetable because if I just use truncation, I end up with a very steppy waveform coming out, and those steps are going to introduce high frequency components. So you see on the graph, it would produce a lot of aliasing and audible noise. The interpolation technique is much smoother, although you can see a few artifacts at the higher frequencies. Even with interpolation, the number of elements in the table is important. You can imagine if we used interpolation and had 4 elements in the table, we would end up with just a triangle wave. That would produce a lot of high frequency components in the output sound, and we could end up with even more aliasing and audible noise. So I ran a simulation to see what the spectrum would look like with different sizes. 32 and 64 both produce a lot of artifacts. So I went with 256, which is a good compromise between size and clarity of sound. Given the time, there are a few improvements I could make to this product. One is adding a MIDI interface so that I could generate sound externally. I already have the velocities of strumming and know which notes are being pressed. That would be easy to convert into the digital information needed for MIDI. I would also like to have live instrument voice selection, so you could adjust the timbre with some buttons. You could play notes as if you were a piano, a saxophone, or any other instrument, perhaps even some more electronic-y sounds. I'd also like to productionize this design with some printed circuit boards. Space was a constraint in this project, however the actual chips are quite small, and I feel like the form factor could be brought down significantly. I also think a more efficient hardware abstraction library could allow a better deployment on other devices. The STM32 HAL is very nice for usability, but it is very general purpose, and it could be more efficient. Thank you for your attention. Please look at a link in the description for a demonstration of this project.